Today we are going to learn about mastering Q learning, reinforcement basics, focusing on how to implement Q learning in practical scenarios, and understanding its fundamental concepts. Welcome to the video on mastering Q learning, reinforcement basics. In this video, we will dive into Q learning, a key algorithm in reinforcement learning. Q learning helps agents learn optimal actions to take in various situations by exploring the environment and learning from the consequences of their actions. It is a trial and error method that enables an agent to learn from past experiences to improve future performance. We'll explore the significance of Q learning in artificial intelligence and how it enables machines to adapt and make decisions autonomously. By the end of this video, you will understand the core components of Q learning, including the Q table, states, actions, and rewards, and how to practically implement Q learning in Python. Let's get started on this fascinating journey into the world of reinforcement learning.
Reinforcement learning, RL, is a subset of machine learning where an agent learns to make decisions by performing actions and receiving feedback from the environment. Unlike supervised learning, where the model learns from a labeled dataset, RL focuses on learning from the consequences of actions, often through trial and error. The core idea is to maximize cumulative reward over time. An agent interacts with the environment by taking actions that lead to different states, and each action results in a reward or penalty. The agent's goal is to learn a policy that maximizes the expected cumulative reward. RL has numerous applications, including autonomous driving, robotic control, and game playing. Understanding RL is crucial for developing intelligent systems that can adapt and optimize their behavior based on feedback. In this section, we'll explore how RL differs from other types of learning and set the stage for diving deeper into Q learning.
A Q table is a crucial component in Q learning, representing the knowledge the agent has about the environment. It is essentially a matrix where each cell corresponds to a state-action pair, denoting the expected future rewards that can be obtained from taking a specific action in a given state. The Q value is an estimate of the potential reward, and the Q table guides the agent's decisions by suggesting the best actions to take in various states. At the start, the Q table is often initialized with arbitrary values, and it is updated iteratively as the agent interacts with the environment. The goal is to learn optimal Q values that lead to the best policy. Understanding the Q table concept is vital because it forms the backbone of the Q learning algorithm, enabling an agent to learn from experience and improve its decision-making capabilities over time. The exploration versus exploitation dilemma is a fundamental challenge in reinforcement learning. Exploration involves trying new actions to discover their effects, while exploitation focuses on leveraging known actions to maximize rewards. Striking the right balance between exploration and exploitation is crucial for efficient learning. Too much exploration may lead to unnecessary actions and slow learning, while excessive exploitation might cause the agent to miss better strategies. Common strategies to balance this dilemma include epsilon-greedy policies, where the agent explores randomly with a small probability, epsilon, and exploits the best-known action otherwise. Understanding this balance is essential for designing agents that learn efficiently and effectively adapt to their environment.
In Q learning, defining states, actions, and rewards is critical to shaping the learning environment. A state represents a specific situation the agent can be in, while actions are possible moves or decisions the agent can make. Rewards are feedback signals indicating how good or bad the outcomes of actions are. Properly defining these elements is crucial for effective learning. States should be comprehensive enough to capture relevant information, actions should cover all potential decisions, and rewards should align with the desired outcomes. Designing an effective reward system is often a challenging task, requiring careful consideration to ensure the agent learns the intended behavior. By understanding how to define states, actions, and rewards, you can set the foundation for successful Q learning implementation. The Bellman Equation is a cornerstone of Q learning, providing a mathematical framework to update Q values. It relates the value of a state-action pair to the immediate reward and the expected future rewards. The equation is as follows: Q state, action, equals 1, alpha, Q state, action, plus alpha, reward plus gamma max Q next underscore state, all underscore actions. Here, alpha is the learning rate, gamma is the discount factor, and the goal is to minimize the error between the current Q value and the target value. This process, known as temporal difference learning, allows the agent to learn from the difference between predicted and actual rewards. Understanding and implementing the Bellman equation is key to ensuring the Q learning algorithm converges to the optimal policy. Let's translate our understanding of Q learning into a practical implementation using Python. We'll start by setting up an environment, such as OpenAI's Gym, which provides a platform for developing and comparing reinforcement learning algorithms. Next, we'll code the Q learning algorithm, initializing the Q table, and iteratively updating it using the Bellman equation as the agent interacts with the environment. We'll define the learning parameters, including the learning rate, discount factor, and exploration strategy. As the agent learns, we'll observe the Q table's evolution and analyze the results to ensure the agent converges to the optimal policy. This hands-on experience will solidify your understanding of Q learning and empower you to implement it in various scenarios. Implementing Q learning often presents several challenges. Overfitting can occur when the agent memorizes actions instead of learning general strategies. Large state spaces can overwhelm the Q table, requiring function approximation techniques like deep Q learning. Sparse rewards make it difficult for the agent to learn meaningful strategies, necessitating reward shaping or using techniques like reward sparsification. Balancing exploration and exploitation is a persistent dilemma that requires fine-tuning exploration strategies. Additionally, debugging and tuning parameters like the learning rate and discount factor are crucial for achieving stable convergence. By understanding these common challenges and their solutions, you'll be better equipped to implement robust Q-learning agents.
Q-learning has a wide array of real-world applications, demonstrating its versatility and effectiveness. In autonomous vehicles, Q-learning is used to make real-time decisions for navigation and obstacle avoidance. In robotics, it helps in controlling robotic arms and enabling them to learn complex tasks through interaction. Game playing, such as training AI to play chess or Go, utilizes Q-learning to develop strategies that rival human expertise. In finance, Q-learning models are employed for market prediction and portfolio optimization. Personalized recommendation systems also leverage Q-learning to suggest content based on user interactions. These applications highlight the transformative potential of Q-learning in various fields, showcasing its ability to solve complex decision-making problems. In conclusion, we've explored the foundational aspects of Q-learning, a pivotal algorithm in reinforcement learning. Understanding the Q table, balancing exploration and exploitation, and implementing the Bellman equation are crucial steps in mastering Q-learning. We've discussed practical implementation in Python and addressed common challenges and their solutions. Q-learning's applications, from autonomous vehicles to personalized recommendations, demonstrate its immense potential in AI. As you continue your learning journey, I encourage you to explore more advanced topics in reinforcement learning and experiment with implementing Q-learning in diverse scenarios. Thank you for joining us, and best of luck in your future endeavors with Q-learning.